Next is applying principle of minimum potential energy to solve for the deflection at B. Eventually we'll get the deflection of E2. For the spring system, the strain energy of the spring system is half K delta square, where K is the stiffness and delta is the deflection. Okay, we are given a spring system in which we have two springs that are connected in a series with each other. So it is, we have to the second spring a load P is applied, and we have to find the deflection point P. And we'll see that we can also find the deflection point A. So here it is explicitly mentioned that we have to use principle of minimum potential energy. So what we'll do is we'll find the potential energy first. That is, we know the total potential energy is defined as pi is equal to U minus W, where U is the strain energy and W is the work done. Okay, so to find the strain energy, we just have to we have been given here that the strain energy is half K into delta square. Now two springs have two different stiffness K1 and K2. So we just have to gauge out the deflection. So we have two springs, we have a load here PB. If we look at the deflection, this is point B, this point A. If we look at the free body diagram, this thing, or if we just look at the system, if we consider that this is inside a black box something, then due to this load, the point B will move an amount, say xb. I have no delta. I'm using x here. If you find that confusing, pardon me. So I'm using xb here. So that will be the deflection of point B. So we don't know anything about what's going inside. So we just know that point B deflected xb. So this is a series system. That is, the springs are connected in series. So this spring is going to pull the spring, and thus the point A will move a distance of xa. Okay, and point B obviously will be moving a distance of xb. So this end is fixed. So the net deflection of point of the spring is xa, and the net deflection of the spring is xb minus xa. That is, xb minus xa is the net deflection of spring 2. So from what we have here, we just apply it. That is, the strain energy of the spring A is half K1 xa square, and the strain energy of the spring B is half K2 xp minus xa whole square. Okay. Now the work done is given by load into displacement. So in this system, as I mentioned before, if we put this in a black box, the load has caused deflection of xb. So pardon me here, this should be xb. This is equal to pxb. Okay, so that's the work done. So what we can see here is we can define the total potential energy as pi is equal to U minus W, potential energy minus work done. So this will be x. Okay. So by the principle of minimum potential energy, we for a system to be stable, the second derivative should be less than 0. Yeah, so the second derivative should be less than 0, and the potential energy should be minimum. Okay, so in each case, each deflection should give a minimum value. So so for that, we just differentiate pi with respect to xa and pi with respect to xb. So this will represent the minimum value for each of them. So as we have parameters here, we just differentiate them. We'll get two equations. We can differentiate that. That's a pretty straightforward differentiation. We'll get A and two equations A and B. So we can see that as we have xb here, we will have P here and xa. So we have parameters xk and xp here, so we can solve this out. We just sum them up, xb terms will cancel out, so we will get pa is equal to xa is equal to p by k1 and xb is equal to, substitute xa in either of these terms, we will get the value of xp. So thus we can find the deflection of point a and point b.